Hello and welcome back to your Chem 4 lecture. This week we're starting chapter 7 on the mole and mole relationships. So it's a new type of mole that you probably haven't heard of before, but this mole is going to be a really useful way to describe large numbers of atoms in a sample of a compound. So like for example, if you have like a gram's worth of something, the number of atoms that you actually have is enormous because atoms are so small. So if you were to say you have a gram of iron atoms, well, the actual amount of atoms that you have is beyond counting because the number itself is so large. So we come up with a number that helps us kind of shorten. And the way that you can think about this number, the mole, is think of it like the way that we use a dozen. Like, do you go to the store to pick up one egg? No. You go to the store to pick up a dozen eggs, or maybe a half dozen if you don't use eggs very much. And we know that a dozen is 12 eggs. There's also cases, you have cases of cans, there's reams of paper, for example. And Avogadro's number describes the mole, which we'll take a look at here on the next slide. So this number is a huge number, of course, because we're talking about atoms, which are very small. It is 6.02 times 10 to the 23. And that is that is Avogadro's number. So 1 mole of something, of anything, would contain 6.02 times 10 to the 23rd items. Now, if you were actually to write it out, you'd get something like this. Again, just an enormous number that's kind of beyond our, comprehension or, normal utility. But when you're describing things that are very small, this number becomes very handy. And this number was invented around the time that atomic theory came into vogue in chemistry in the early 1800s. And credit for the number is given to Amedeo Avogadro, who was an Italian physicist who was corresponding with a lot of different chemists at the time, including Dalton, who we talked about before, and then many of the people who were working on gas laws at the time, which we'll talk about in the next chapter. Okay, so now the idea of a mole is, with a mole, now we can convert from a mole to the number of atoms or the number of items of a particular compound or element. If you have 1 mole of an element, that means that you have Avogadro's number worth of atoms of that element. So 1 mole of carbon would give you 6.02 times 10 to the 23rd atoms of carbon. 1 mole of sodium would contain 6.02 times 10 to the 23rd atoms of sodium. But that's not where it stops. You could also have, for example, a mole of a compound, like water. If you have 1 mole of water, that means that you have Avogadro's number, 6.02 times 10 to the 23rd molecules of that compound. Same thing for CO2 or vitamin C here, for example. Sodium chloride is an ionic compound. If you say that you have 1 mole of sodium chloride, that means that you have 6.02 times 10 to the 23rd formula units of sodium chloride. And remember, the formula units are just representative, kind of the smallest charge balanced unit within an ionic compound. For sodium chloride, that would be 1 atom of sodium, 1 atom of chloride. Okay, so that means that we can do conversion factors, right? If we have an equality that we write like this, well, then we know that we have 2 different conversion factors. There's 1 mole per 6.02 times 10 to the 23rd particles, or 6.02 times 10 to the 23rd particles per mole. Now, that's extremely useful for reasons that we're going to see very soon. Now, it might seem just kind of like a random number, but as we're about to find out, the number itself is really useful for converting a large quantity in mass from grams to molecules. Okay, so let's do an example problem here to kind of get ourselves thinking in the right way. Avogadro's number is used to convert moles of a substance to particles. How many CO2 molecules are in 0.50 moles of CO2? Well, just like all of our problems, we should analyze what we're given and what we're asked for. We're starting from 0.50 moles of CO2, and we're asked to give the number of molecules. We need to know that the connection between moles and molecules is going to be Avogadro's number. So now we're ready to write our conversion factor. We know that 1 mole of CO2 is equal to 6.02 times 10 to the 23rd molecules of CO2. So we can set up a conversion factor where 6.02 times 10 to the 23rd molecules of CO2 per 1 mole of CO2 allows us to convert directly from the 0.50 moles to the molecules of CO2, just like that. Okay, so why don't you go ahead and give it a try now. What is the number of atoms that are in 2.0 moles of aluminum? Go ahead, pause the video here, and when you come back, we'll look through the answers. Go ahead, give it a pause. Okay, now let's take a look at the answer. If you're given the number of moles of aluminum and you're asked to find the number of atoms of aluminum, you should know that the connection between the two is Avogadro's number, or 6.02 times 10 to the 23rd. And we know that Avogadro's number is going to allow us to convert from moles of something to atoms of something, like aluminum, using the equivalents like this. 1 mole of aluminum equals 6.02 times 10 to the 23rd atoms of aluminum. Well, we just have to set up the conversion factor so that moles of aluminum are canceled out. That gives us 2.0 moles of aluminum times 6.02 times 10 to the 23rd atoms of aluminum divided by 1 mole of aluminum. Solve for significant figures here, you end up with 1.2 times 10 to the 24th atoms of aluminum. Okay, now let's do the reverse way. What is the number of moles of sulfur in 1.8 times 10 to the 24th atoms of sulfur? Pause the video, work it out, and then we'll look at it when we come back. So pause. Okay, let's give it a shot. Well, once again, now we're converting from atoms to moles. So the key conversion factor is going to be Avogadro's number. If we have the 1.8 times 10 to the 24th atoms of sulfur, and we need to get to moles of sulfur, well, then we need to multiply by 1 mole of sulfur per 6.02 times 10 to the 23rd atoms of sulfur. In this case, it's going to be 1.8 times 10 to the 24th divided by 6.02 times 10 to the 23rd, and you end up with 3.0 moles of sulfur. Okay, so that's for just straight elements, and that's pretty straightforward. Now we're going to think about the relationships that are given to us by a chemical formula. So we spent a lot of time in the last chapter discussing chemical formula so that we understand what this means. Now, then we talked about it in terms of a molecule. Aspirin, for example, has a molecular formula C9H8O4. For one molecule, that means that we have 9 atoms of carbon, 8 atoms of hydrogen, and 4 atoms of oxygen. But that's not the only way that we can think about it. In fact, we also have mole relationships that are given to us here. If we have 1 mole of aspirin, that means we have 1 mole of molecules that are all C9H8O4. So if we have 1 mole of aspirin, that means that we have 9 moles of carbon atoms. Also means we have 8 moles of hydrogen atoms, and finally, 4 moles of oxygen atoms. Now we can use these as conversion factors. We know that we have 9 moles of carbon atoms for every 1 mole of aspirin, C9H8O4. Likewise, you could say that you have 1 mole of aspirin for every 4 moles of oxygen. These are all examples of conversion factors that you can write given a molecular formula. Okay, so why don't you go ahead and give it a shot and answer the question, how many atoms of oxygen are in, notice this, it says how many atoms of oxygen are in 0.150 mole of aspirin, C9H8O4. So go ahead, pause the video, try to think it out. This is a 2-step problem, but once you get there, we'll unpause the video and we'll look through the answers. So go ahead, pause. And we're back. So in order to get from moles of aspirin to atoms of oxygen, we need to convert from moles of aspirin to moles of oxygen using the chemical formula. Then, once we have that, moles of oxygen, we can use Avogadro's number to convert to atoms of oxygen. Well, the subscript is given to us here. We know that we have 4 moles of oxygen for every 1 mole of aspirin because it's in the formula, C9H8O4. 4 atoms of oxygen for every 1 molecule. Likewise, 4 moles of oxygen for every 1 mole. And then to convert to the number of atoms, we just need Avogadro's number. We know that there's 6.02 times 10 to the 23rd atoms of oxygen for every 1 mole of oxygen. Plug it into our calculator. It's 0.150 times 4 times 6.02 times 10 to the 23rd. That gives us a final answer of 3.61 times 10 to the 23rd. Okay, so that's the mole. And those are very useful conversions, but as you can imagine, it's just kind of a trick if you're just converting from the number of atoms to the number of moles. It doesn't really mean anything. What really matters for the mole is the molar mass. And the molar mass of an element is the quantity in grams that equals the atomic mass of that. So this is going to be on the periodic table, for example. Look at sodium here. We have its atomic number up here. Of course, that's the number of protons in the nucleus. And we have its atomic weight down here. Now, in the last chapter, we described this as an average weight of one atom of sodium. So 22.99 atomic mass units for one atom of sodium. But that's not the only way that this is useful. And this is why the mole is so useful. If we have 1 mole of sodium atoms, that mass in grams is 22.99 grams. So now we have a second use for this atomic weight. So here it is. A molar mass is the mass of 1 mole of that element. So 1 mole of carbon, of course, means Avogadro's number worth of carbon atoms. And it's also the atomic mass expressed in grams. So there's just an extremely easy conversion factor that's provided to you on the periodic table that we're going to be using for the rest of the semester. So for example, carbon, its atomic weight is 12.01. That means that if we have 1 mole of carbon atoms, that mass is 12.01 grams. And guess what? If we have an equivalence like this, that means that we have a conversion factor or 2 conversion factors. Now, for our textbook and what we have on the periodic table for our tests, we round the molar mass to the hundredths place, or we use 4 significant figures when we have our calculations. So just so you know, that's how we get these masses here. They may differ a little bit if you have a different periodic table or you search it online. There may be more significant figures, but just for clarity, we try to keep it to the 2 decimal places. Okay, now let's compare. So if we have 1 mole of sulfur, it takes up about this much space here. 1 mole of iron takes this much space. 1 mole of sodium chloride takes about this much space. 1 mole of potassium dichromate takes up this much space. And then finally, 1 mole of sugar takes up this much space. Now, there's a few interesting things here. You might ask yourself, why is sulfur taking up more space than iron for 1 mole? Well, there's a few things with that, right? Remember, basically, iron is going to be more dense than sulfur because it's got more mass packed in a smaller volume. It makes sense that sodium chloride would be a little bit take up more space because it has, 2 ions for every 1 atom of iron. Think of it this way: it's 1 mole of sodium chloride contains 1 mole of sodium ions and 1 mole of chloride ions. Likewise, potassium dichromate, even more atoms. And then finally, sugar, a very large molecule, has many, many atoms. Okay, now let's go through how we're going to calculate molar mass. And I realize I need my calculator, so I'm going to pause the video. I'll be right back. Also, a good idea to have a periodic table with you now as we go through this. It's just going to help out a lot. Okay, so here's a question. Calculate the molar mass for lithium carbonate used to treat bipolar disorder. This is something that you're going to be expected to be able to do very quickly, from now on throughout the semester. So always a good idea to get some practice. Now, lithium carbonate, if we know we've got lithium ion, which is Li+, plus carbonate, which is CO3 2-. Bring them together, you need 2 of the lithium ions, Li2, CO3, and that gives us lithium carbonate. Now, the formula Li2CO3 gives us all the elements that we need in order to calculate the molar mass for each element. So let's go ahead and give an example. Now, if we know that we have lithium in the compound, we can look up lithium in our periodic table. It ends up being 6.941 grams per mole of lithium, 12.01 grams per mole of carbon, and 16.00 grams per mole of oxygen. Now, we don't just add those together. We have to take into account how many of each that we have. And for that, we need to use the chemical formula. So we have 2 lithiums. So we take 2 times the molar mass of lithium. And I just normally keep these in my calculator. So I'll say exactly how I put it in my calculator. So 2 times 6.941 plus we have 1 carbon, so that's 1 times 12.01 plus, then we've got 3 moles of oxygen, so plus 3 times 16.00. Add all those together, and you end up with 73.89 grams per mole. In other words, the molar mass of lithium carbonate is 73.89 grams. Okay, now why don't you try it? Give it a shot. I have a molecule here, C2H6O, could be ethanol, probably ethanol. Give it a try, find the molar mass, and then we will show how to go through it in just a second. So pause the video here, work it out, and then we'll show you how to do it again when you come back. Pause. And we're back. Okay, so if we have a formula of C2H6O, well, we know that our elements are carbon, hydrogen, oxygen. Carbon has a molar mass of 12.01 grams per mole. Hydrogen has a molar mass of 1.01 grams per mole. And oxygen has a molar mass of 16.00 grams per mole. Our balanced chemical formula, or I'm sorry, our chemical formula contains 2 moles of carbon. So we put in 2 times its molar mass, so 2 times 12.01 plus 6 times hydrogen, right? So 6 times 1.01 plus 1 times 16 for the oxygen. And we end up with 46.08 grams. So it's just that easy. As long as you have a periodic table, it's pretty quick to calculate these. Okay, now that's molar mass. But what's really important with molar mass is the types of calculations that we can actually do. Now, with molar mass, this is the key connecting point from the mass of a substance to the number of atoms of that substance. The mass of the substance is something that's really easy for us to measure. That's what's crucial, is we can measure that on a macroscopic scale. The amount of, like the number of molecules, that's what's really important on a chemical scale. That's going to tell us how many molecules are reacting, and that's what's important there. Okay, so molar mass conversion factors are extremely useful, as I mentioned. So if you take methane, for example, and find the molar mass, well, it's 1 times carbon plus 4 times hydrogen. That would give you a final mass of 16.05 grams of methane per 1 mole of methane. Oops, sorry. So then you could use that as a conversion factor, whether that's going from grams of methane to moles of methane, or vice versa, moles of methane to grams of methane. Both can be useful in given circumstances. Okay, now let's do an example calculation. Let's say that a box of salt contains 737 grams of sodium chloride. Let's ask ourselves how many moles of sodium chloride are present in the box. Okay, so we're going from grams to moles. What's the key thing that we need to know about sodium chloride? The key connecting part is the molar mass. Given the molar mass, we can convert directly from grams of sodium chloride to moles of sodium chloride. Let's give it a shot. So sodium chloride is NaCl. That means that we've got 1 mole of sodium, so 1 times 22.99, plus 1 mole of chlorine, that's 35.45, for a total of 58.44 grams per mole of sodium chloride. Now it's just a matter of aligning the correct conversion factor. If we start from 736.7 grams of sodium chloride, well, we know there's 1 mole of sodium chloride per 58.44 grams. Grams cancel out. When we divide 737 by 58.44, we get our answer in 12.6 moles of sodium chloride. Okay, time for a sample exercise. A sample of water has a mass of 59.8 grams. How many moles of water are in the sample? So just to make sure it's not a trick question, just remember water's molecular formula, H2O, and you won't go wrong. So go ahead, give it a shot, pause the video. Okay, I'll assume you're back now. Let's go ahead and do the calculation together. So the first thing that you know is I'm converting from grams to moles. And the key conversion factor is going to be the molar mass. So if we take our grams of water and find the molar mass of water, we should be able to convert it to moles of water. Well, we have H2O is our molecular formula. So that's 2 times hydrogen, 1.01, plus 1 times oxygen, which is 16. That gives us a total of 18.02 grams per mole. In other words, 18.02 grams of water per 1 mole of water, or 1 mole of water per 18.02 grams. Now, then all you have to do is do the calculation, starting from 59.8 grams of water. There's 1 mole of water per 18.02 grams of water. That gives you a total of 3.32 moles of water. Okay, well, now we have a whole solution map that we can use. We know that from the moles of the element, we can either convert to atoms or ions of an element, or grams of an element. If we use molar mass, we can get to the number of atoms using Avogadro's number. Converting from moles of a compound to moles of an element, that's using formula subscripts. Grams of a compound to moles of a compound, that's a molar mass problem. And then finally, moles of a compound to molecules of a compound, that's Avogadro's number. So we have all of these different ways that we can map out problems. Okay, well, that does it for today. We have more of these problems in the next section moving forward in this chapter, chapter 7. So I'll see you soon with that. And of course, always ask in the comments down below if you have any other questions. Until then, bye-bye.